Thank you very much. Good afternoon, ladies and gentlemen. And it is my honor, it is my pleasure to share with you about my experience and the lessons I learned and the observations I have regarding the fundamental research, technical innovation, and startups. First, I give you a little bit outline what I will cover in my presentation. And the first thing I want to talk is the difference in science and technology. And the second topic will be synergistic research across two arenas. And then we will talk about the research for startups. And of course, there are more than technology itself. And we kind of all know the science and technology are different. And the science basically focus on the discovery and understanding of phenomena or mechanism behind. For example, if we observe double rainbows with concentric semicircles, but with the opposite spectrum, and if we understand, we discover those things, this is the science or the scientist care about. And another example is the old faithful geysers. And the water erupts every 90 minutes. And why it happens in this way, it is the science issue. And of course, engineering is less romantic or less exciting, and it is more detail-oriented. For example, the London Bridge. And as you can see, it involves a lot of details. And you need to have a very good design, construction, and every detail work out very well. And the bridge need to last very long and reliably functioning. And of course, here give you another example and about an airplane. And the airplane involves very many parts, and every part has its own functionalities, and it should be very well designed and fabricated and assembled together and make it work. And of course, science and technology are inseparable and they are all connected. Just like in our research, we do science and technology all together. And if we take another example, like the diamond, the natural diamond we have here, and what you see, they have different colors, and they have different shape. And if you make a polishing and a cut to the diamond jewelry, and you will see they are very different. And this is a process of we can consider as engineering or the technique. We need to convert the raw diamond to the jewelry. And if we want to have a better understanding, we need to go back to the science part. What is the diamond? Diamond actually is a pure carbon. And the carbon is the same as what we have in our pencil. And it's number 6 element. And surprisingly, actually, diamond is not stable at ambient environment. It is only stable at high pressure, high temperature. The natural diamond is formed in the very deep in the earth and under very high pressure, high temperature. And when the science develops, the people's understanding getting better, and actually now we also can grow diamond at a lower pressure, actually under vacuum, low pressure and a very high temperature. We also can grow diamond, and those are scientific issues, and those are the conditions. As you can see, you can grow diamond, even thermodynamically, they are not favorable, and they are supposed not stable. And let's take a step back to look at how to make the diamond jewelry. And the subtitle, actually, the science is the foundation to make those diamond jewelry. And if you recall your experience, you see all those diamond jewelry, you never see a jewelry in a spherical shape or raindrop type of diamond. They are always faceted. And there are very big reasons or scientific issues behind. And typically, or always, the diamond are designed with a specific angle, specific size or ratio. And the reason they do so is because you want to make sure the light comes in from any angle to this piece of diamond jewelry. It will come out from the top, so the diamond jewelry will be really shining. And to make those internal, the total internal refraction, and so the really good quality diamond will appear like that. Even you have the white color shine on the diamond, it will become self-colored. And the reason is because the white light has different wavelengths. They travel in a very different speed. Now, if they have the total internal refraction, and the white color goes in together, and when they come out, they will separate to different wavelengths. And that's why they become colored. So for any research, for technical innovation, and for startup company, for high tech, you need to have a good scholarship and a very good fundamental research. And here, my title says, balance your research. Even your focus is to do the innovation for startup, but in the beginning, you still need to focus on your scholarship. And for myself, over the years, actually 17 years at UW, I have written and edited 7 books and published a number of journal papers and preceding papers. And I also presented over 200 technical talks and seminars. And we still have a number of patents pending. And we graduated or supervised over 100 people in my lab in the last 17 and a half years. Now, actually, if you do the fundamental research and industrial research or technical research, if you combine them together, it can be really synergistic and it can be really beneficial. And for example, if we look at the industrial project, their focus is to solve very practical technical problems, and they're very specific, very focused. They are typically short-term and no desire for any publications. However, if we look at the fundamental research, you are looking for broad impact knowledge, and you want to have it will help you build up the solid foundation for new invention. And it typically is a long-term effort. And if you do the industry project as a fundamental research, you will build the foundation as well for the knowledge. And fundamental research typically emphasizes the publications. And the benefit from industrial project, first thing you will learn is a very different perspectives. And it solves the real world problem, and you learn how to communicate with people with less science and technology background, and typically like business people. And if you do the fundamental research, you will establish a broad basis of knowledge, and you become an intellectual resources for industry. And you will learn how to run simple, straightforward, cost-effective research, and it also, in turn, later will help you when you start a company. And here I give you 2 examples and about the industrial project that we did. The very first one is a hard coating on optical polymer filters. And we used the organically modified ceramic coating because the polymer does not allow us to heat to high temperature. And the maximum temperature it can tolerate is 150 degrees C. And the requirement was from the industry Actually, it was from ferroelectrics. It's a Seattle-based company. They wanted to make the ceramic coating on the optical polymer filter. And they tested the requirement is they put a diamond pane and a scratch on the surface 10 times. The optical transparency does not decrease. So it was their requirement. And as you can imagine, if you apply a ceramic coating on the surface, you meet this requirement. You do not have any publications. However, if you have the fundamental research in mind, you definitely can make a fundamental research here. What we did here is we look at different chemical compositions. The base composition is silica. We introduced the organics. We introduced the transition metal oxide, and we use the chemical solution method to make ceramic coatings. And this curve tells you the hardness, the surface hardness really changes significantly and based on different composition. And actually, after applying the ceramic coating, the hardness can increase about 1 order of magnitude. Actually, the polymer, the hardness is about 0.2 gigapascal. So any composition we applied, we already exceed the requirement of the industry. However, for us, we still want to push forward to get a fundamental understanding for publication to establish the long-term expertise for our group. So we not only studied different composition, we look at the hardness as a function of the depth. What we can see on the second slide, actually the hardness not only is determined by the surface or the coating, it's also by the substrate. And if you make the same coating on a hard substrate, the surface is harder. If you apply the same coating on soft substrate, the hardness is lower. So that actually was one of the first findings in the entire community about such kind of phenomena. And later we also look at some heat treatment. As I mentioned, we use the solution method to make a ceramic coating. If you don't have any treatment, and you get the hardness 1.1 gigapascal, and if you shine the UV light onto it, the hardness increases, and if you heat at 150 degrees for 30 minutes, the hardness increases as well. And those increase actually is the result of the densification. And what you can see as the heat treatment changed from no treatment to UV to low temperature heat, and the hardness increases, the thickness actually decreases. And this is involved with the microstructure and the low temperature centering. And all those things actually tells us the chemical composition, the annealing condition, and the thickness all can have the impact on the hardness of the coating. And of course, you can easily summarize those things, give a good explanation, and make nice publications. And the next example or the project that we run is the corrosion protection coatings on metal wires. And this is for biomedical application and for Boston Scientific. And the metal wire need to be flexible, and the ceramic coating need to be thin, since there is a big difference in thermal expansion coefficient. Ceramic coating also cannot be centered at high temperature. Now, the typical corrosion resistance research is you put a corrosive agent onto the material, and you put their weight 1 week, 2 weeks, or 1 month, 2 months, see what happens. And if you see there is nothing happened or no visible or appreciable corrosion in a week or 2 weeks, you are done with your project. And this is what the industry cares, but from the fundamental research point of view, we want to have much better understanding. So we use the electrochemical method to characterize those coatings. And the first curve here shows if you have metal with coating and without a coating. The first thing you'll notice, those two curves are very different. And without a coating, the corrosion occurs very rapidly. And corrosion you can consider as an electrochemical reaction involves the transfer of electrons. So if the current density is high, means there is a big corrosion going on. And now if the corrosion is small or no corrosion, and those are the current density, this is in logarithm scale. So from here to here, this is like 5 orders of magnitude if you apply the ceramic coating there. And of course, the voltage reflects how harsh the corrosion environment is. If you have the coating, you really can survive in a very harsh corrosive environment. And basically, there's no corrosion at all. And we went further, since we use the soil or make the solution to make ceramic coating, and we compared the freshly made soil or solution to make a coating, or we weighted a little bit, and what you can see, their corrosion resistance really differs, again, very significantly. And not only the current density changes quite a bit, and also the ability to stand the corrosive environment also changed a lot. So again, here we show the chemical composition process and condition, aging or not aging, and we also have tested if we flex those wire on the metal, how the corrosion resistant property will survive. And of course, we managed to have some good publication as well. So what I try to show you in those two cases, with very, very simple industry project, you still can do very good fundamental research. And fundamental research will build up your reputation, and you will gain a lot of knowledge, experience. And other people like Boston Scientific, they come back to me for 3 projects again and again. And even some projects I did not have any experience, they say, well, we trust you, you will figure out the way to solve those problems. I say, no, but if you give me money, I will be happy to take it. So it is also you learn very different perspectives. And they only care about solve the problem. If you have other understanding, that's your opinion. They don't really care. But if you demonstrate you can have fundamental understanding, it will give them a very good impression. They will come back to you. And also, it will help you with different ways of thinking, and you have the connections to industries. Over the years, at least I got like 5 or 10 people I did not know. They come to knock my office, and they say, Dr. Cao, I heard your student give a presentation, or I saw your publication, and I have a little money. If you like, I can sponsor your research. And I always say, yeah, I would love to have those things. But I don't take the big money, I take smaller money. You can do a lot of research. Big money is too big pressure, the responsibility there. And of course, the industry will connect you to the investors. The investors actually, they invest more on the people than on the technology. This is, not many people realize that. You have a good technology, but if you don't have a good management team, they are not going to put money on your hands. And a startup actually is a totally different challenge. For the science, I mentioned, you discover, you have a good understanding, that's it. For the technology, you need to make it reliable. You build a London Bridge, it must last 100 years. You know, if you build build a bridge for 1 day, you can take a picture, you demonstrate you can do it. That's fine, but how it lasts, that's the engineering issue. And over the years, we experienced 4 startup companies. The very first one is Energy2. The name started with Energy2 in 2005. Actually, company started in, earlier than that. And later, we also started a company called Living Green Materials, which is for dye-sensitized solar cells. And again, we have another project called CNC Material, try to commercialize lithium-ion battery material. And I also involved with another company called Lumiscent, and we try to commercialize silicon quantum dots for light-emitting diodes. And I share with you the experience or the history about Energy2. Aaron Fever actually was a student, and he, at that time, still had a job at a Boeing company, and he went to join my group in the autumn quarter of 2003, and he made it very clear the first time we discussed. He said, I want to have my own company. I said, that's fine. And he said, all my PhD research went to develop a technology for a startup company. I said, that's totally fine with me. So we started with some materials for hydrogen storage, as it was a very big hype for hydrogen economy. And we collaborated with a scientist at Pacific Northwest National Lab, Tom Autry, and he also got a nanotechnology fellowship because we did not have any funding. We really started with the idea, I want to have a company. And about a half year later, Rick and Chris, they contacted our then department chair, Raj Baudia. They wanted to form a company to start to work on the clean energy as a high-tech company. So 3 of them formed a company, and we started to apply for WTC funding over a period of 3 years. We got in total $240,000. That's all the funding we got for the Energy2. And later, I also introduced Bill Scott, who is the retired professor from our department, so they can try to write proposals for SBIR, STTR, but we never got one. And so Energy2, actually, we begin no technology, nothing at all. And so we started to work on the so-called coherent, porous, nanocomposite of hydrogen storage in 2004. And we did get very good results scientifically from fundamental point of view. We can tune the temperature for the hydrogen to release, which is technically very significant. And we published some papers and have patent application, and we did get patents. And then we realized if you have the hydrogen storage material, you have the technology, the market is not there. It depends to many other factors. And the commercialization is a long way down the road. So we went back and told the WTC, it will not work, but we still want to keep the company business going. And what we try to do, we want to use those porous carbon to store natural gas or other gases. And it will reduce the pressure from those stainless cylinder quite significantly, from, for example, 150 atmosphere to 30 atmosphere without sacrifice the volume. And after like 6-9 months, we realized the industry actually are very protective, and they refuse the penetration or take the new technology there. And we also realized the natural gas storage the market is quite small at that time. And then we went back to WTC, we told them another story. Say we have nice porous carbon, we wanted to commercialize for supercapacitors. And they agreed with us because Aaron, me, Rick, Chris, 4 of us as a team did a very good job and convinced those panel we can do it. So that is the reason the Energy2 moved out from my lab. Actually, as a supercapacitor company. And they moved out from my lab actually in the Christmas holiday 2008 because they got a big investment. And before that, actually they did not have anything. And so for the technology, if you're ever going to look for commercialization, you want to look at the cost-effective technology, and the technology can be scaled up for mass production. And then you also need to realize market is really important. And if you have technology, even you are capable to move the technology ahead, don't push too much. For example, like the transistors, miniaturization, you need to follow the need of the market. You don't over-push it. And actually, there is another core issue, is the people. And you need to have the right person, and you need, for example, Aaron Fever, he was really self-driven. He really determined to have his own company, and he works day and night. Well, he took a lot of vacations and hiking, camping, but he took it as his own business. This is really important. It is not for advisors, not for the department. And of course, money is really important. If you have money, you can switch to different business. And of course, everything you do, you need to have a good luck. And here, I give you a little bit my observation or what I learned during the years. Actually, you probably all know there are two famous canals in the world. And one is the Suez Canal, and which is 202 miles long initially, and opened like 150 years ago by a French businessman. And later, there is a Panama Canal. It's only 48 miles, and it opened in 1914, and 50 years later. So both canals are fully functioning. And interestingly, the Panama Canal actually was first attempted by the same French businessman and by the same company. They got a successful experience, and they got a successful business, they got money, and they tried to dig Panama Canal. And this is what they tried to do, and they did not succeed. And they lost a big amount of money, and they lost a lot of lives. And the company bankrupted, and the French business also got charged with corruption, etc. But he managed to get away because he was old. And then the Americans take over, and they built a very different canal. And what they did, instead they built the sea level canal, they built the canal above the sea level. And you can find all those stories from Wikipedia, and it is a very good lesson to know. The technology need to be improved, or innovation need to have a continued innovation for new challenge, new environment. And of course, another lessons we can find. We all know today in Bay Area we have Silicon Valley, and our life are all relied on the electronics. The very first one, the company started Silicon Valley, is called Shockley Semiconductor Laboratory. It was founded in 1956. And at the same year, Shockley, together with his former colleagues, won Nobel Prize. And they got a big investment from Beckman Instrument. Beckman is a Caltech professor, and he invented pH meter, and he made a lot of money there. And in addition, Shockley also got a big backup from Thurman, and he was the Stanford provost and dean of engineering. If you want to start up a company, you cannot imagine anything better than that. But this company, if you look at the history, they did not make a single money, single dollars. And the original laboratory site now become a produce market. So you have investment, knowledge, all the things does not guarantee you are successful. And it's just about a year after the Shockley laboratory was formed, 8 key people resigned all together, and they formed a Fairchild. And now we don't have Fairchild, but we do have Silicon Valley, and we all know there is a company called Intel, and there is a company also called AMD. And they did a kind of survey about 65 companies in Silicon Valley, actually initially from Shockley Laboratory. So the market is there, technology is needed, but you need to have something beyond the technology. And you can read a lot of things online, and there are books about if you ever want to start a company. And the technology is not everything, even the money, the investment. And what I try to convince you now here is we can do well in both fundamental research and technology innovation. And I want to thank you. And I will be happy to answer questions.
Can you talk a little bit about how Aaron figured out what he would like to start his company about?
Could you repeat?
How did Aaron settle in on what he would like to start? How did he come up with the ideas of what the possibilities were?
Well, actually, when Aaron started, we had a conversation late afternoon. I forget it was Friday or one of those late afternoons. He said in my office, he said, Dr. Cao, I'd like to join your research group. I said, you're welcome. And he continued, he said, I know you want your student to become a professor, but I don't want. I say, well, that's fine. I don't expect that every of my graduate students become professor. And he said, I asked, what do you want? He said, I want to have my own company. And that was the beginning. And then we realized, and he said he wanted to have the company about hydrogen storage. And he did not have a clear idea what to do. And actually at that time, there was an article published in Nature. It's the carbon nanotube can store a lot of hydrogen. And that was his idea. He wanted to follow this idea to develop a carbon material to store a lot of hydrogen. And of course, if you follow the hydrogen storage or carbon nanotube, you realize that paper published in Nature actually was false. It was a mistake. And carbon nanotube never can store a lot of hydrogen. And I got a confirmation from the first author, and she said it was a mistake in person. I asked her, and she confirmed. And in the community, we all know that. And so Aaron started with the carbon, and very soon we realized it would not work. So since I also, we do the fundamental research, and we realize for carbon, you only have the physical absorption of hydrogen there, and it is very difficult. So we try to have the chemical storage through form compound there. And if you form compound, then the problem is how to, you need to control the release of hydrogen. And when you release hydrogen from a compound, it's just like a decomposition, and the temperature will drop. Now the issue is, if you release hydrogen, the temperature drops, the chemical reaction will stop. That means if you do develop a material for hydrogen storage, you use this hydrogen to empower your engine in your car. You drive your car, and you push the gas and release more hydrogen, and the material, the temperature drops. They will stop, release more hydrogen. Your car will be dead. So when we realized that, we thought, if we mix those compounds with carbon, carbon is a very good conductor, thermal conductor. So if you need a lot of heat, the carbon can introduce or conduct a lot of heat in it, and the carbon is also a good electrical conductor. So we can have the electrical conductivity to heat the materials up. So that was the reason we pushed the composites. So it is a simple technical issue, but if you know a lot of fundamental issues, you can have combine them together. So that was the first reason we call coherent nanoporous carbon composite for hydrogen storage. And we demonstrated actually for the hydrides or for the chemical compound, we can control the pore size. And when we reduce the pore size, we reduce the crystal size of the chemical compound. And by reduce the size, we can reduce the temperature of chemical reaction. And we can reduce from, let's say, 200 degrees C to 80 degrees C. So it is very fundamental issue. And if we do have in the future, we come back to the hydrogen economy, those ideas were still perfectly fine. So, and that was the starting point.
So you have up there, you can do well in both fundamental research and technology innovation, but you've also said that's not all that you need to successfully move into innovative companies.
Right.
So can you put a label on those skills that are those extra added labels?
Well, this is, you need to have the fundamentals so you can gradually, you have enough knowledge, experience, you can tackle the technical challenges. And if you develop a skill to deal with the practical challenges, and then you can have the technology for startup. But the startup, as I mentioned, like a Shockley laboratory, the technology obviously is there, right? That's why we still have Intel, we can have all those fancy electronics. The problem is you need to have the ability to hold the people. The people are willing to work for you. And the people is really the critical issue. You know, you are very rich, you are very powerful. The people may scared of you, but not necessarily respect you. They love your money, but not necessarily love you as a person, as their leader. So it is really important, and I think the management skill, the ability to hold the people or to mobilize the people to, you know, the one issue is your vision and the ability to share with other people. This is really important. And just for example, there is a book called Crystal Fire. It is about the transistors invention and about Shockley Laboratory. And there is a lot of good analysis there. It is the people and a good team. And there is a danger if you start a company, you may lose your friends, right? For example, like Bill Gates and Paul Allen, I heard they were very good friends and hang out during the weekend night in the computer science and engineering building. And well, I don't know if they are still friends, right? So if there is a money issue, it is very different. And if you publish, you put yourself as first author, second author, or another professor as the corresponding author, it is not a big deal. But if you have the money issue, then you need to really look at good people. And when we formed a company called Living Green Material, and we had 4 people to form the company, and one young gentleman from New York, and he has a very good philosophy. He said, you know, we need to share the benefit with everyone involved that can give us support. if the company is successful, if I get 5% of the company, that's more than enough I need. You don't hold 75 or 80%. You let other people to share the fortune. Not many people can do that, because if you don't have money in front of you, you can easily give us such a talk. And if there is money, I just want to keep as much as I could. And then the company will not survive. Yeah.
From the Energy 2 experience, it seems like you're kind of constantly ahead of the market, and you end up searching some of the areas. Hydrogen is still not really taken off, natural gas is too soon.
Right.
Is there any advice to the working industry to actually find out that you truly are addressing their current near-term needs to really keep off the number?
Yeah, it is. There are a lot of fancy technology you can develop, but not all the technology are very useful. And what we did with Energy 2 at that time, and we really identify the market need. So Aaron worked on, in the laboratory, and I generated a lot of ideas. And Rick and Chris, they going around to talk with business people and investors and what is the market and everything there. And when we, at that time, we make a proposal to WTC and to angel investors and VCs, and 4 of us go together. And it seems a lot of investors like the combination 4 of us, and because we can answer most questions collectively, and seems that's really important. And at that time, actually, it is a lot of conventional wisdom said you need to stick on your technology, but what we stick to is the porous carbon we developed, and we only changed the application, the emphasis, the smaller part. So the porous carbon is our critical issue, or the material there. We can say, if we have the porous carbon, we can manipulate it, we can control the porous structure, the chemical composition to the point we need for application. So for hydrogen, we needed to introduce the hydrides there. For natural gas storage, we only modified the surface chemistry. And for the supercapacitor, it's the same thing, the porous structure and the chemistry. So it is not too difficult for the panel to accept our arguments, and we demonstrated any project, even we decide not continue for commercialization, we have a beautiful fundamental research and a technical understanding. So the people see we really make the progress. The money they give to us is small, but we make a big progress, and they had the feeling if they give money, we will produce something. And that's probably is one big issue keep us going.
So how's the company, where's it at now? So it's 2008.
Well, after 2008, actually they moved out, and then very much we have the separation, and they keep working on their company, and I work on my research, and it was another story actually. After they moved out, and they got more and more money, and from also DOE money, and one day Rick called me back, and he tried very hard to convince me he can give me, our lab, a big amount of money, and I should do the research to solve their technical problems. But at that point, I was very clear. I said, I don't want. The reason is, they promised to give me a big amount of money, like $2 million, $3 million per year. Now, this is too much for me. And well, I love money. If money go to my personal bank account, I will be happy legally. And the issue is, I can see the danger down the road. If I got a $2 million in my research group, I will put all other research aside. I just do the research for the company. Now, 2 years later, either I solve the problem or I don't solve the problem. What will be my research group going? And I did not want to have this. And after the clear separation from them, then I can develop new technology and I can do my own fundamental research. And for example, the carbon-related material, I have a very close collaboration with another company called Uni Energy Technology. They work on the flow battery, and I try to develop the new carbon electrodes for them. So if I still have a very close relationship with energy too, I would not be able to do that. So there are always certain things you need to make clear what you really want, and not in the first year, second year, 5 years, 10 years. That's you need to foresee what are the potential problems.
If there's no more questions right away. Oh, sorry.
Yeah.
I have a question. You mentioned about for the natural gas storage,
Mhm.
that market was difficult to penetrate.
Right.
Can you be a little bit more specific to elaborate on that area?
Well, at that time, the issue is the natural gas storage at that time by the stainless steel cylinders. And since such kind of technology is very mature, and if you want to develop a new technology, you can reduce the pressure there, so you can store the same amount of energy there. But the stainless steel cylinders, you need to put porous carbon into it. So whole the manufacturing process will be different. So they don't like to make those changes. If the company makes a good money, why do you change? Just like if you have a good job with a good income, you're not looking for a new jobs, right? If you're not happy with your income and with your colleague or your boss, then you're looking for new jobs. So that's the same thing.
One of the things you've mentioned that really resonates is the willingness to pivot during your research, and I believe Energy 2 continued to have to pivot as they figured out what the market really wanted. And I think that's something we see with successful teams, and why the people are so important is the path you think you're going to take is never the one that you really do end up on.
Yeah, with the industry, like when Aaron was in my group, and we really realized we love to have the company, and we have a love with hydrogen storage, but when we realize it is not going to be successful, we switch to the natural gas, to supercapacitors, for whatever. It is different, but the research we did with the porous carbon, that's the foundation we had, and can keep us going.
Thank you.
Thank you very much.